see later on. Okay, so yesterday we had a simple transistor from the library and we wanted to see its S parameters. So now let me tell you something. Okay, if you place these supplies, okay, directly without an inductor, right? So what are you showing to this transistor? You are showing a short. Okay, so basically, if I was to put a Smith chart, right? So I'm not going to plot anything. Okay, so if, for example, you take a device, a big device, okay, and okay, you took a big device and you didn't use this inductor. You just were plotting the DC characteristics, right? And I directly connected the supplies to the drain. Okay, okay, so let's wait for the screen to be visible. I hope today we won't have a problem. Let me push this to pause and fix this. Okay, okay. So what we did was we took a 100 micron device, right? And what I was trying to explain you was that if you do not use these inductors for decoupling, then these supplies are DCs, right? So they are going to look as RF short. So basically you are showing impedance here, right? You are showing impedance over here. Okay. Now, is that a problem? Well, when the transistor becomes large, right, you have got these circles, okay, which you call stability circles, right? Okay, and it might happen that this point may be unstable, right? This point may be unstable. So what are the chances of what are the points? Okay, so these are all the impedance points, right? So this is a short, okay, and this is an open circuit, right? Okay, so this is an open circuit and that's a short circuit. Now these two are very notorious points. Okay, so whenever people do DC characteristics, they would just directly connect the supply to to the drain and the gate, and they will do a DC plot. But how do you know that the transistor was stable at the short, right? Maybe the transistor is not stable at the short and it will just keep oscillating. So when this transistor starts oscillating, all your DC characteristics are wrong. Okay, so this is something which I try to tell many people, but they don't believe me. They just say, okay, let's put here the supply and this supply and then just sweep them and just plot the output and transfer characteristics. But when the transistor becomes big, it tends to become unstable. So when it tends to become unstable, it oscillates, then the DC current drawn is going to be much higher. So your DC curves are going to be wrong. So the right way of taking DC characteristics is show some impedance which is expected to be stable. And the one which is stable is farthest away from the periphery. So what is the farthest away from periphery is the center, right? So if you could terminate this transistor into 50 ohm and then look for the DC characteristics, there are more chances that the transistor will not oscillate. And what you will have is a stable transistor, and the transfer characteristics and output characteristics will make sense, right? So people, what they do is they don't do decoupling, they don't do coupling, and they don't do termination, and they just do the DC curves. And in large transistors, this is not correct. Even in the lab, when you go and measure this on a parameter, analyzer, you'll find that large transistors tend to oscillate. So you need to terminate them in proper impedance, right, before you take the DC characteristics. So that's what I used to do. Okay, so now how do you first decouple this? Okay, so you want a short. So of course, this is a short, and this inductor should be large enough to transform it to open. So basically, the short would be transformed to open. Okay, so that's how the decoupling works, right? So if you are not sure, you can even put a capacitor. Okay, so what will happen in real life? These supplies will not be short. Actually, they would have some certain internal resistance. So when you do it practically in the lab, what you want to do is you want to have a capacitor hanging to ground here and capacitor hanging to ground here, because these DC supplies usually have internal resistance, right? So the transistor is going to see those impedances which are going to be small. So rather, what I'll do is I would make sure that I have a capacitor here. So whom should I admit? There are two of them with the same name, twin brothers. Okay. So what I'm going to do is at this frequency, even 0.2, 0.3, 0.4 picofarad is like a bypass gap. Okay. So let's make this, let's say 12 and let's say 12. Okay. So 12, 12 would be, these are the dimensions. So this is this much, not good enough. Well, I can make a bigger one, 20 and 20. Okay, so this is like 0.4 picofarad and 30 would be. So this is the maximum size this PDK is allowing you on a capacitor. So that's 900. Okay, so the issue using large capacitors or inductors are that you have to make sure that they are not resonating or anti-resonating. Okay, so I'm going to use this size. So whenever you use large capacitors at high frequency, make sure through EM simulation that they are not resonating or anti-resonating. So they haven't reached their self-resonant frequency. That's what I'm trying to say here. So I'm going to put two capacitors here. Okay. And then, of course, now there is a basic difference between CMOS, SIGE, and gas and GaN. The problem is in CMOS SIGE, we don't have a real ground, in the sense the ground is coming through bond wires, okay? Because there are no vias. Why? Because silicon and silicon germanium, they are conductive, electrically conductive. So when they are electrically conductive, so am I doing a mistake here? Let me admit him also. Maybe I don't know who is for him, which one is working. Okay. Okay. So what happens is there are no vias in silicon germanium. So if there are no vias, then the ground is coming through a bond wire inductance, right? So let's assume that it is coming through a bond wire inductance. So go to lump components and insert a small inductance in here. Maybe it is like, something like 100 nanohenry, 100 picohenry is good enough. That represents a bond wire inductance. Okay, so let's put them there. Okay. So basically, these capacitors are not seeing the ground. They are seeing an inductive ground. The reason is silicon germanium doesn't have vias with very low inductance. That's the major problem. Second, same thing situation is going to come here, right? When you try to do this, okay, of course, you are not going to see a very good ground here. And the reason is very simple, because there are no vias in silicon germanium. So let's say I put here 40 picohenry. So what you do is for DC, that's fine. For bypass, you might have a longer wires, but this one decides the gain. Okay, so basically, if you were to have the what you call the source, and if you want to ground the source, right, you have to use many bond wires, not just one or two, right? In academics, I see people doing this, that they come with the chip layout and everything, and they say, oh, there is only one pad for the source ground. That one pad for the source ground is not good enough, right? You might have to put lots of bond wires to get certain gain out of this. And at high frequency, this becomes very important because the source inductance cannot be large. If it is large, well, there will be no gain at high frequency, right? So source has to be grounded properly with many wires. Now the question comes is how many wires? Okay, so let me just go to a place where I can write. Okay, so I would say grounding. Okay, these are important concepts here. Grounding. Okay, so let's assume that I have a pad. This pad is on the chip, and I somehow can do. Usually they say 100 micron by 100 micron pads. I can put many of them, right? Okay, or I can have, if some processes allow you to do a big pad, that's fine. Then I am going to have, this thing is going to see a ground, and problem is the back of the chip is not the ground. Because it is a conductive substrate, right? If it is a conductive substrate, you can ground it, but that would be a very poor ground. And to bring it, the only way is the bond wires. Okay, so let's say this is the edge of the chip. Okay, so this is the edge of the chip. Okay, and these are the pads on the chip for ground. And let's say if I introduce one thing which is like, a pad which is part of the package, right? So I'm going to put lots of ground, lots of this, what you call, okay, just bear with me. Okay, so I'm going to put lots of bond wires here, right? So, and I'm doing this for a reason. Okay, so I'm going to put lots of ground wires here. Okay, and insert shape. Oh, come on. Insert shape. Okay. Oh, all people are two of them. Okay. Okay. This is important. Why this is important is I'll tell you. Okay. So basically, of course, this is a wrong drawing, not to the scale. So basically, this is going to be much bigger than the pads on the chip. Okay. So let's say if you do a ground like this, right, for your CMOS chip, right? So ground comes in from the package. Of course, the package has a ground at the bottom. That's good for taking out heat. Okay, that's good for taking out heat, but electrically it's a poor ground. The only way, so there are no VRs in silicon germanium. So no VRs in silicon germanium. No VRs. Okay, in silicon / silicon germanium. Okay, so if there are VRs like gallium arsenide, gallium nitride, you are sitting on a very good ground. But if you don't have a VR, then you are sitting on a ground which is coming through bond wires. Now you should know some things. Okay, these wires are usually 1 mil. Okay, 1 mil dia. Okay, so these are like gold wires, 1 mil dia. In production, this is usually not better than 13 mils, the length. 13 mils / 1 mil dia. Okay, 13 mil / 1 mil dia. Now, in lots of defense projects where they come and they say, okay, we want much lower inductance, okay, or any high frequency, we need much more inductance. So how to reduce inductance? Of course, so if you use the same 1 mil dia wires, so let's not have a confusion. Okay, so if you put 1 mil dia wires here, right, and they are commercially 30 mil long. And second thing you should know that these are not going to be wedge bond. So these are going to be ball bond. Okay, so what do you mean by ball bond? Of course, the edge, the ends of the wires can look like edges. Okay, so how would I draw that? I want to give you a full view. So for example, I'm going from a chip to this thing, and this thing is a bond wire, right? So the edges, okay, so the edges are going to be like this. Sorry. So basically, I'm drawing the same wire only. I'm not filling it. Sorry. Okay, later I'll shrink it. Doesn't matter. So this is your bond wire. And okay, so basically the edges. So edges are like these wedges. Okay, so this is like a wedge. Okay, so the bonder detaches and then it smears the bond wire onto the pad. So this is called edge bond. Okay, so this is an edge bond. Okay, so I will name this as edge bond or wedge bond. So the bonders can be wedge bonders. Okay, so all your what you do, what you call, whatever prototyping you are doing, these wedge bonders are available. They are cheap, and then there are something called ball bonders. So the ball bond looks like this. So you have a wire, okay, and this wire is not going to terminate like that. Okay, so let's see. So that's the wire. And this thing is going to be like a ball, something of this nature. And there is going to be another one. There's going to be a ball over here. Okay, so this would be called the ball bond. Okay, now we know that chip has a certain height. Insert shape. Okay, so basically this is the chip edge. So this is from the side view. Okay, and in this case, this is your chip edge, and this is how it's going to sit. And this is going to be a pad on the board or on the package or whatever. Okay, so this chip height is something which basically is contributing to the length of the wire. Now, what these okay, so now what is going to happen is this usually is going to be, so if I take a silicon or silicon germanium process, right? In that case, the wafers are thinned down. So let's say the wafers are 300 mil. So usually this height is around 300 mil. So this height is around 300 mil. Okay. So this height is around 300 mil, and this wafer is thinned down to 300 mil. Okay. Now, currently the wafer is around 12-inch dia wafer, and the thickness of the wafer is 300 mil. That's fine. Okay, but these days they can also mill it down the backside of the wafer down to 100 mil. Okay, so that means that this height is reducing to 100 mil. That means that this wire basically is slightly reduced in length, but this advantage is not there in silicon germanium. This doesn't make a lot of advantage in case of gallium arsenide, or let's say gallium nitride. Okay, if I thin down to 50 mil, for example, so this is, so if I thin down to 50 mil, okay, and why would I be able to thin down? Because these wafers are like 6-inch wafers or 4-inch wafers. Okay, gallium arsenides are going to be like 4-inch wafers or 6-inch wafers. Okay, so I'm talking about gallium arsenide and gallium nitride. Okay, so usually these wafers are 4-inch, and they can be thin down, okay, they can be grounded down to 50 mil height. And what is the advantage? The via which sits in here, okay. So, okay, so basically there is a via which sits in here, right, like this. And okay, so this is the via which is sitting in here, which is going up to the top, up to the circuit. Okay, so now thinning of the wafer has an advantage over here because the height of the via is going to shrink by the thickness of the wafer, right? So basically we are saying that this is, if I thin down to 50 mil, okay, so sorry, if I thin down to 50 mil, okay, so that is basically sorry, not mils, I put microns, so I'm doing mistake here. Micrometer, so it is 2 mil actually. Micrometer, sorry. Okay, so usually silicon germanium, the wafers are around 12 inch and they are around 300 micron in thickness, right? And they can, if you ask a foundry, they can ground it down. But in silicon germanium, all the contacts are coming through bond wires. And then there are two kinds of bond wires, wedge bond and ball bond. Okay, so wedge bonds are available for your prototyping, but wedge bonds are not available for production. So basically in production, you only have ball bond. And in ball bond, the minimum dimension for a ball bond wire, the length of the wires is 13 mil. So if you demand a inductance much smaller than that, you go to any packaging house. Okay, Atmel is very famous. So if you go to Atmel and you say, I want less than 13 mil, they would not say no. They would say, yes, we can do it. But then they would have to do a lot of circus here. Okay, they have to do a lot of circus here, and I'll explain you what the circus is. Okay, so we were doing CGA amplifiers and we were doing all this circus with Atmel, okay, with IBM. Now in gallium arsenide, gallium nitride, this is straightforward. If you keep thinning the wafer down, and that you can do because the wafer is 4 inch or 6 inch, you can thin it down to 50 micron or 2 mil, then that means that your vias are going to be 2 mil or 50 micron tall. So the ground inductances are going to be much smaller. The gain of the devices are going to be higher, right? So that's the advantage of GaAs and GaN is you can do, because these are insulating substrates. These are dielectrics, while these silicon germanium are conductive. Okay, silicon germanium are conductive, so you cannot put vias. Okay, you have to bring them through. You have to bring them through wires. Okay, so the gain of the devices is going to suffer now because the wires are in production 13 mil long. Okay, now if you ask for a smaller inductance, they would not let you. So in that case, you are left with adding more wires. Now, adding more wires, is it advantageous? Yes, the self inductance is going to be in parallel and it will come down. But the issue is, and we did this with all kinds of experiments in IBM. Okay, the issue is the following. Okay, if I keep on increasing the number of wires, okay, so if I say n is the number of wires and I keep increasing it, so basically n is the number of wires on x-axis. Okay, so if I keep on increasing the number of wires, the inductance, okay, the inductance basically is going to do this. The inductance basically starts somewhere around 300. So for this kind of length, so it is going to start with something like 0.6 or 0.7 nanohenry. Okay, so it will keep dropping with the number actually it will keep dropping with n increasing. Okay, and after some time, I see that there will be no effect of n. N is the number of wires. Okay, and on this side there is inductance L. Okay, so this is self-inductance plus the mutual inductance. Sorry. Self-inductance plus the mutual inductance. And this inductance keeps dropping as I increase n. And beyond 9, okay, no matter what angles you do. So basically, you can always do these wires at angles. So when you do these wires at angles, then the inductance goes down. okay, because the mutual inductance goes down. So when you put these wires, let's say 9 of them or 10 of them, the inductance comes down to like 0.2 nanohenry, okay, which is 200 picohenry. Okay, so this comes down to something like 200 picohenry. 200 picohenry. Okay, so 9 wires or 8 wires, because the self inductance is going to be cutting out because they are in parallel, but the mutual inductance is going to go up, right? So what's going to happen is you have to space them apart. You cannot just bunch them together. You have to space them apart. So if you want to go below 200 picohenry, you would need more wires. And second thing, you should also know that the heat in this case is also coming out through bond wires. Why? Because this silicon is doesn't have a metal at the back of this. So in silicon, there is no back metal. So when there is no back metal, what do? You basically epoxy. With a conductive epoxy, you take the chip and epoxy it to the bottom ground of the package. And the problem is that's a good electrical conductor, but thermally, it's not good. Epoxy thermally is not going to be good. So the heat will not go through the bottom of the chip. The heat will go only through the wires. So now you are faced with another problem here. If you put just one wire, you will not be able to take heat out of it. You have to put more wires. So silicon germanium is a little problematic when you go in watts. So we were doing GSM PAs, which is like 2.5 watts at an efficiency of 50%, right? So basically that means that 4.5 watts, so 2 or 3 watts is going as a heat. So how do you take 2-3 watts out? Okay, the only way is through bond wires because there are no vias here. And the back is not plated. So when the back is not plated, metal plated, then you cannot solder it down. The chip is epoxied down with a conductive epoxy. So it's a good electrical conductor, but it's a poor thermal conductor, epoxy. So then the heat will not go through the bottom of the chip, but the heat has to go out through the wires, right? So this is something which is practical. You see, you will not see in LNAs, but you will see in PAs. Okay, so this is something which you will not find in the books. Okay, and you will have to experiment and learn this. Okay, so now what will people do? They'll say, I want to lower inductance. So now you are going to take a chip and flip it out. Okay, so you have a flip chip. Okay, so now you have a flip chip technology here. So all the silicon and silicon germanium, you'll find that they have flip chip technology and they are sitting on a ball grid. So let me say insert shape this. Okay, so they are sitting on these balls. Okay, so these are also called C4 bumps. Okay, so they are sitting on these balls, and their inductance is much smaller. Okay, so these inductances are much smaller. Okay, but then there is a restriction on the pitch between the balls. Okay, so if you put lots of balls for bringing a good ground, less inductive ground to the chip, okay, so the circuit sits on this side only. Okay, so you basically flip the chip and then there are C4 bumps here. Fine, this is good. But the problem is when you do a 2-watt PA, this is going to melt as the thing goes to heat. All the heat is going through these balls, and this is going to melt, and this chip is going to start floating. As you hit it with power, the chip is floating. Now the IBM came up with something called slab technology. So this is going to, for PAs, this is going to sit on a slab. So if you are doing SIGE, which is Global Foundries, you can ask them to do a slab. Okay, so the slab would be like, there will be slabs like this. Okay, and then this can sit on slabs. Okay, now, can this solve the problem? No, it is going to heat and the slab is going to melt, and this thing is going to just float around on these molten tin. Okay, so this is tin only. Lead is not allowed because you will not clear the specification. It has to be lead free. So if this is tin, then what they do is around these balls or around this slab, they are going to put a cap so that even if it floats, even if it melts, the cap is going to restrain the molten tin. Okay, so this thing sits there. So earlier in my career, in 1999, 2000, yeah, 2000 I started. 2000, by the end of 2000, I was doing flip chips, and these flip chips have PAs have problem because PA would start floating on this because I was taking out like 2 watts of power out of GSM PA. So the PA would start floating. Okay, so these practical problems are there with silicon germanium. Flip chip is one technology. Then shorting then okay, there were some designers who said, oh, we still don't want to do flip chip, we want the bond wires. Now how do you reduce the inductance? Okay, so they did ball on ball bond. So basically this ball, then you break the wire, then another ball sits there, and then top of the ball comes to the height of the wafer, and then you do a direct bond like this. So there is no loop like this. Okay, now if you go to Atmel and say, can you do this in production process, they would say yes. But then the package, which was like 30 cents or 40 cents or maybe a dollar, will look like $2. Okay, so in commercial, this is not viable that you can have a $2 packaging, okay, or $1 packaging. Okay, if this is 30 cents, then you have to do 30 cents apart packaging. Okay, so all these things you should keep in mind when you are doing silicon and silicon germanium. Sorry, I need to group them. Okay, so when you are doing silicon germanium, you have to keep this in mind, that grounding is not coming through vias. Grounding is coming through wires. If you flip it, the chip, you are sitting on balls. Okay, and then if you take heat out, then there is a problem of this. Okay, and heat will not go through wafer because silicon germanium is epoxied. It is not soldered. While in case of gallium arsenide, because this is a insulator, you can put these vias, substrate vias, and the back plate basically is a metal. So there is a back plate which is a metal. So let me just do that so that it looks like a metal. So basically the back plate is metal. Okay, so there is a back plating on gallium arsenide. Okay, with this back plating is not there in silicon germanium. Okay, so these are the grounding issues. So I took a lot of time, but when you are designing, okay, when you are a fresher or when you are sitting in India, for example, Indians don't see this process. Indians see a package part. That's it. They see a black colored plastic package part. It may be a no lead package, but it's still a plastic package. And they don't know what is going on inside, because let it be TI or let it be any other, they don't think about this stuff because they don't do it. They just get a package part. So when I came in 2003, when I came back, TI was establishing their RF division there, and they invited me to advise them. And I asked them, what are you going to do with the bare die? They said, we don't get bare die, we get the package part. I said, in RF, you are going to work with package parts. And that was the major flaw there with TI. And they had to close down their RF division. Okay. And same thing happened with Intel. Okay. They came and said, we will do Wi-Fi, WiMAX integrated into our chip. And then they burned their hands because they have no idea about RF. Okay. So that's the problem, okay, with India, is they don't see half the story. They see just this thing. When they just see this thing, they become ignorant of what's going to happen here, and they design with, they don't put this here, okay, they design with this, and they say, oh, my chip has come back, it is not working. Of course it will not work, because what about the inductance? You didn't take into account the inductance, right? Okay, you are not aware that that's what's happening. And second thing, even if it works, you don't know about heat. You never planned your package with the heat, right? So how is it going to work? Okay, so that's the major problem for past 15 years with India, is they see just the pretty package stuff which looks pretty, They don't know the ugly stuff which is inside to make it work. And they don't want to reform this because the manager sitting there with 20, 30 years experience, they have just done this. Okay, so if I go to DRDO, LRDE in 1999, the guy would just sit on this or a layout. He would have no idea of how to take the heat out or how to do with the inductance, what to do with the inductance. So that was not included in the design. And then when it comes back, this happened with Astra. Okay, Astra Microwave Products, they did Allen and they say, oh, our this thing, noise figures are not right, and when we model it is very bad, and this and that. Of course, you didn't take this into account, and your designers, I saw their schematic, they didn't have anything into account. And then they said, oh, the transistor models are really bad. Let's buy a load pull and do our own transistor model. That happens with the 30-year-old experienced guy in India. Okay, they blame it on the model. They don't blame it on their stuff. And they say, let's spend 300,000 more to buy a load pull, to buy a probe station from Cascade. That's what happened with Astra Microwave Products. Okay, so that's because they haven't looked into the ugly picture here. And they haven't included this. If my professor used to say, if it is in the real life, you have to have it in simulation. If you don't have it in simulation, then your thing will not work. That's a fact. So if it is in real life, it has to be in the model. Now, I'll tell you one more example. It's a diversion. Okay, I had a 0402 component, or those SMD components for the board. I was doing an evaluation board for my MIC, and I put here, let's say this one. Okay, what I did this. I put 2 pads for the SMD components like this. Okay, and I was working at 5 gigahertz, and I made it exactly to the size. Okay, and I did the EM simulation. And my professor said, this is wrong. These pads have to be bigger. Right? These pads have to be bigger because you are doing Z current modeling. Okay, if you have a discontinuity here and your SMD sits right at the edge, how the simulator models the Z current? So you have to bring these pads bigger, and the component should fit on this. And then you can model the Z currents in your EM simulation. So if it is there in reality, it has to be there in your simulation. Okay, you cannot be an ignorant guy and then say, oh, let's blame it on model. That's wrong. Okay, so that's what I have observed in 15 years in India. Okay, these things, the IBM guys or Intel guys abroad, they won't ignore this. This is the bread and butter. They can't ignore this. It has to work. Okay, in India, we can scrape the project and say we can't do it, but that's not over there. Okay, we cannot scrape it. I'll tell you lots of things with SIGE, which you cannot just take the model and just design it at 80, 90 gigahertz and then say, oh, my amplifier is blowing up cold, hot and cold, it's blowing up. Why? You have to picture the die and see which parts are blowing up and why they are blowing up. You have to reason it. Okay, so problem here with the TI guys would be they will get a package part, and the amplifier would blow up, and they say, oh, it is blowing up, and they discuss with 10 people, it is blowing up, but they have no idea why it is blowing up because they haven't gone into SIGE to a device level and to the thermal modeling of the transistor, the coupling of the fingers thermally and all that. Okay, they haven't worked with ballasting also. So they may be doing at 90 gigahertz and think that they are the king of the world, but they don't know the process. And then their amplifier blows up under mismatch or hot and cold cycles. The problem is ignorance. Okay, so that's the thing. That's what is happening in India is when you go to a company which has a fab of its own, you know the process inside out. When you work with a company which is just a design house, you don't know what is going on inside out. That's the problem with Indian design houses. Okay, so let's go forward. Okay, so grounding, this you understood. Now let's go back to our schematic. I placed something over here. This will also do your, this is going to be feedback at high frequency. Okay, and what this means is that the gain is going to go down and this is going to look more stable. So this is a high frequency stabilization. You will have another form of stabilization. So why am I talking of stabilization? If the device is not stable, you don't talk about gain. Your gain is useless if device is unstable. So let's look at this part. Okay, so okay, so what I'm going to do is I'm going to put a capacitor and a resistor. Okay, so let's say high res poly, and I want to put something like 800 ohm resistor. Okay, now another thing which happens, okay, this I have seen with many designers, okay, in SAC. Okay, they say, oh, resistor 800 ohms, well and fine. What about the width? What about the current carrying capacity? What about how many VRs are being used to connect to this? Because resistor fails, okay, if the current density suddenly shoots up through a resistor and it fails, your circuit fails. So a guy would just do, oh, 600 nano, fine. Let's put a 800 ohm resistor here and that's it. No. What about the current capability? Right? So I am worried about current carrying capacity. I don't want this to blow up and my circuit to fail. Of course, in feedback, it doesn't matter because there is no current flowing through this. Okay, there is going to be a capacitor here. Yeah, but if you use resistors or if you use any component, you should know how many VRs you are putting or what is the width of the trace. You have to worry about current carrying capability, right? So let's make a capacitor of like 0.3, 0.4 picofarad as a feedback capacitor. Okay, now I'll tell you why. When will these things blow up? I'll tell you. So this is 148. 20. And then some processes allow you to do capacitors which are irregular shape. Okay, then people would, they are doing layout and somewhere they need a capacitor, they will just squeeze in a capacitor which is rectangular. So horrible. They will make a capacitor which is boot shaped. When I see that in layout, I am horrified. I look at their face. Okay, when you make a rectangular capacitor, have you done something called, have you simulated currents on a capacitor? Do you know where the capacitor fails? The capacitor fails on the corners. And why it fails on the corners? Because all the currents is crowded on the corner. If you make a square, then the current density on the corners is less. So when I started my career in ISC, okay, and I did a capacitor in my design, my advisor put me to do conformal mapping and using conformal mapping to figure out the current on the capacitor. And then he said, okay, do a rectangular capacitor, do a square capacitor, and then see what is the current density on the corners. And the rectangular capacitor has more current density on the corners, it's more likely to fail. Okay, so in India, we don't think about this. Okay, while if you go to anywhere else, you will say, okay, square capacitor, I'm not going to go other than the square capacitor. Now, I had a chance to work with 2-3 more engineers who had their chips in Nokia phone, and they are very much particular about layouts. Okay, it's not that in US you have a 4-year degree on layouts. Okay, and the layout designer has gone through a 4-year bachelor's degree. In India, the layout is like, okay, anybody can do it, it's just a drawing. No, it is not a drawing, it's a drawing with certain rules, right? So you have to be careful about that. So now this is also a high frequency feedback. Now what it is doing, this is called lead compensation. It'll take a right hand side 0 and put it on the left hand side. So there are 2 poles there. Okay, so one is going to be the dominant pole, other is going to be the second pole. So when you introduce a zero in between, it will give you a phase plus 90, while the gain would roll by minus 20 dB per decade. So it will improve your phase margin. So this is called what you call lead compensation. So this is a lead compensation here. Okay, so this is again a high frequency feedback. This is a low frequency feed. This is also a high frequency feedback. Now, the transistors, they become big. They oscillate at low frequency, not at high frequency. Okay, so in that case, there are these, you can buy these packages, right? The UMS come out with a power bar. And you will see in that power bar, what you will see, or anybody else who is doing this gallium nitride, okay, they sample you a transistor and then they give you an application note, and in that application note they say, to stabilize this, put a 3 ohm resistor here in the RF path. Yeah, it will kill the gain. If you want to do this, for your low frequency stability, you do this. But if you want to do this, do this. Okay, so you buy any transistor from UMS and you get their application note. They'll just put a resistor here. What about this bypass? Okay, this bypass has to be there, no? Okay, so if you buy there what they call the power bar, it comes only with the resistors. What about this cap? You are killing the gain. Okay, you have to kill the gain at low frequency, not at the high frequency. So for high frequency, give a bypass path. Okay, another way of stabilizing this would be put the resistor over here. Okay, so if you put the resistor over here, what's going to happen is that the DC current, well, there is no current because there is this thing, but this resistor is going to give you a low frequency stability. Okay, so these are two ways to have a low frequency stability, and these are the two techniques to have a high frequency stabilization. Okay, now having said that, let's very quickly go and tune this transistor. First, let's look at its S parameters. Okay, let me rotate this. Okay, here let me put the biggest size I can, 30 and 30. And let me remind you, okay, it's very good to be confident. Okay, but just because you have done a high frequency circuit, don't be overconfident. Okay, because frequency is just a number. It's none of your expertise. It's just a number. Okay, and why I'm saying this, because somebody made a comment that what do you know about design? So at this point, after 20 years, somebody is making a comment to me. What do you know about the design? I have done 60 gigahertz, 80 gigahertz, 90 gigahertz design. Okay, and I didn't like that. I told him clearly, frequency is just a number. Okay, so what I'm telling you, listen to what I'm telling you. I'm a PA designer, so I know how to do broadband PAs. Okay, so I didn't like that. Okay, so these are coupling caps. Then you do termination. Okay, so now I'm ready to look at its S parameters. Okay, so let's look in band. Okay, so let's say my band is going to be 27.5, which is the American band, to 28.35. It's not a very large band. And this band is for 5G in America. Let's make this 10 megahertz. Okay, so having done that, I can just simulate this. Okay, don't worry about N sub. That's a modeling issue. S11, S22. So we are over here. So one is over here. The other one is over here. Okay, and let's look at the gain. So it's around 7 dB gain. So all I have to do is bring it up here, bring this one up here. Okay, so let's go ahead and put both impedance as well as admittance. Okay, so all I need is a shunt inductor on the input side to go up this way. And all I need is a smaller capacitor to come down this way. Then that's it. We don't need anything else, right? Okay, one more thing I want to tell you is the following. Okay, these inductors, okay, if they are not large enough, they are part of the tuning. So when they become part of the tuning, then this ground has to be very good. Okay, otherwise the internal impedance of the supplies is going to start affecting you. Okay, it will not affect you in CW, or it will not affect you in your CW. But when you do a modulation, and there are all forms of conversions, then this is going to make your ACPR numbers worse. So you have to have a very good ground over here. Okay, so you have to use sufficient capacitance for bypass here. Okay, if you are in RF, if you are not able to get a sufficient capacitance, so what's going to happen is the following. The capacitors have something called ESR. Okay, that's why you put many capacitors in parallel, because their ESRs are going to come in parallel and they're going to give a very good ground here. It's not that it is a magic that you put here 10 picofarad and then you put 0.1 microfarad and then you put 1 microfarad. No, they are there for a reason. They are not there just because my professor used to say God never plays dice with his fellow beings, so everything has a reason. Okay, so if you put two capacitors here, there has to be a reason for two capacitors. I cannot replace it by one capacitor. So somebody would question, oh, 10 picofarad and then have 0.1 microfarad. So what is the need for 10 picofarad? You have 0.1 microfarad in parallel. Now, your equivalent series resistance has gone down if you put two capacitors here. Okay, so what is going to happen? The short, which was here, okay, so of course I cannot draw very clearly. So short, which was here because of a capacitor, is going to be closer to a short. Okay, so the good short has to be created. Now, if this is not possible through a capacitor, then you better put a stub here. That's why in your MMIC designs, you see a fan here, a radial stub, because that radial stub is giving you a broadband short. Open is transformed to a short. And then you use a λ/4 line to make that short look like an open here. So that's a decoupling. So why do you use that decoupling? Because the capacitors have equivalent series resistance. That's why in MMIC, we will not use a capacitor. We'll use a radial stub and λ/4 line here. Okay, in the books, this is not there. None of the author is telling you this, that I need a very good shot. That's why I have a radial stub and a line. But you go by the convention. MMIC has to be done with a stub. RFIC, I'll use the capacitor. No, that's not the story. The story is I need a very good shot here. That's why. So I would put two capacitors here to reduce the equivalent series resistance. Okay, so that's the point in here. Now, if this is a part of matching, then this ground has to be good. Otherwise, internal impedance of the supplies is going to start affecting your match. Okay, so you have to be clear. Now, if this is a large inductor, then this is decoupling. So if it is decoupling, anyways, a large inductor will come to open circuit for high frequencies. So it's really decoupling is not mattering to you at all, because you are putting a large inductor and it's always open. So in that case, you have a decoupling here. Okay, next thing is people will put a tank circuit here, a capacitor in series with an inductor. Now the problem with that is it is going to roll you fast to the open circuit, but then it is going to roll over. So the bandwidth you are working with is going to be reduced. So if you are doing broadband amplifiers, you cannot put a tank circuit here. If you are doing narrowband amplifier, you can put a tank circuit here and a much smaller inductor so that you can create an open circuit here. If you want to do a broadband, use a large inductor. And if you don't want to use a decoupling here, this is a part of matching, then you have to create a very good short here. Okay, so that's there. Now, let's tune this. Okay, so all I need is this and this. Now, before that, I want to see if it is stable or not. So for that, I need to bring in stability circles. So what are these stability circles? These are contours which join all the impedances where reflection coefficient becomes 1. So now, depending on whether the center of the Smith chart is inside or outside that circle, you can predict which part of the Smith chart is unstable. So where were we? Okay, source stability circle and load stability circles. You don't have to write any equations. Earlier, we didn't have these. So we had to write equations for stability circles. In 2000, when this beta version was released, 1999, I had to write equations for stability circles. They were not there in beta version. Okay, alpha version. They were not there. Okay, so now they are ready-made over here. All you do is simulate. Okay, now here, if I do this, it is going to scale the Smith chart. So Smith chart is over here, right? Okay, so what I'll do is, I don't want to scale the Smith chart. I'll say scale is 1. So now this is your Smith chart, and these circles are way outside. Okay, now when they are way outside, it means that if S11 has a magnitude less than 1, which means that the entire Smith chart is stable. Okay, now once we have established that for load and source that it is stable, then I can use any matching to get to the center. Okay, so let's look at outband stability. So it's not always in-band stability, it's outband stability. So I'm going to go from, let's say, 1 megahertz to, let's say, third harmonic of the highest frequency, let's say 80 gigahertz. Okay, and I am going to, let's say, do as 1 gigahertz. Okay, and I'm looking at outband stability. Okay, now what you see as a line, don't confuse them with a circle, because what happens with ADS is if there is a circle and circle is terminated before, then the graphics is connecting the endpoints. So these lines which you are seeing crossing, okay, these are not circles. They are not part of circles. They are basically the circle was terminated and the graphics couldn't handle that because it was considering a closed loop contour. So they were joining the endpoints with this. If I change the scaling, these lines are going to move. So let's say if I do this as 2. Okay, so now you see these lines are there. These lines are not exactly going to be circles. Okay, circles are over here. These may be the last points which you are connecting. Okay, so whenever I see lines doesn't mean if the line doesn't have a curve to it. Like for example, this line has a curve to it, right? This goes like a curve. So it's a part of a circle. While these are basically the endpoints are just connected, because this is the limitation of graphics of Keysight, this display window, that it cannot do a closed curve with 2 open hands. It cannot have a closed open curve. It has to have a closed curve here. So the endpoints of the circle, they are basically connecting together, right? So let's say if I put this to auto scale.
Anurag, sorry to interrupt you.
Yes.
Why can't we do just the K delta test or mu prime test
Yeah.
instead of?
I'll tell you that. I'll tell you that.
Okay, okay, fine.
Okay.
Sure, yeah, thanks.
Okay.
Yeah.
See, whatever you do here is small signal. Now, we are not supposed to look at a power amplifier from small signal point of view. It may be stable at small signal, but usually when the device compresses, S12, which is the S12 basically drops. So when S12 drops, then the feedbacks are much stronger, right? And under compression, usually the FETs are going to start oscillating, right? So you have to do this thing under power. Okay, so the K, the K should be written with equations where you're putting large signal on the input and a small signal on the output. Okay, so this is like your X parameter stuff. Okay, now where would you find that? So luckily, the old guys of Keysight, or rather HP, they had done it for you. Okay, so over here for LNA, this will not be a question. Let's go for an example. So I'm going to say open an example project. Okay. Okay, so let's say, I don't know, they clubbed this LLSP. And is there a power amplifier? PCSPA, no. HB simulation. This is modeling, this is load pull, and large signal amplifier. Maybe this one. Yeah. Let's open this. Okay. So don't worry about this bad Filvias and all that. Okay. This is the example which has been there for like since the ADS was there, since it was a HP stuff. Okay, so let me try to show you this schematic. Okay, so what are they doing in this workbench? Okay, in this workbench, they are putting large signal on the input and a small signal on the output. Now, one would question, why would you put power into an amplifier from the output port? Yeah, there is no reason for putting a power there. It's just for determining the output impedance. So if I want to determine the output impedance, okay, I would use a small signal on the input side and large signal on the, sorry, small signal on the output side and large signal on the input side. This is what this simulation is doing. And this is called mixed mode simulation. It says SS mixer mode. It's a mixed mode simulation. This is later they bundled this into something called X parameters. And they try to sell X parameters, but this was there for a long time. Okay, and this is the key thing which tells you that load pull is a stupid stuff. Okay, why? Because if you can see the impedances, right, on the output and input, you don't have to do load pull. Okay, only when you don't know the impedances, you do a load pull, right? Okay, when you know the impedances, you do tuning, you don't do load pull. Okay, so that's what this bench establishes, that load pull is not required. You can also do this system in the lab using basically what you call directional couplers. But if you do this in the lab, then what would Mori sell? What would Focus sell? Nothing, right? So every PA designer is given this baggage. Oh, you have to do load pull and source pull. Why? Because you don't know your model, right? Or you don't know your transistor. And then again, do it intelligently. You can put this setup in the lab where you can put in a large signal here and a small signal, and still you will be able to do the impedances. Now, let's say how it is computed. Okay, so if you go here, of course, you know, they change some internal variable, and that intervariable is delta. So delta became a keyword, so they didn't correct this. So now this is correct. So they have computed K using a large signal on the input. So this is HB dot, while this is SM. SM means a small signal. So the output is small signal, the input is large signal, and then S11, S11 is going to be large signal, reflection coefficient kind of stuff. S22 will be small signal, reflection coefficient. And when you work with 2-1, you are looking at a large signal gain. But when you are looking at reverse isolation, you are looking at the small signal. Okay, and then using this mixed mode simulation, you establish your S11, S22 minus S12, S21, that is delta, and then you establish your K. And once you establish your K, you are looking at K under power. So you see the K under power dips under 1. That means that this thing is unstable. Right? This is across frequency, across power. And you can also see how the impedances are moving. So if you remember in my first presentation, I told you that these are going to be like this. And if you do a small signal match, you are basically focusing one part of the curve to the center. That is a small signal match. And under compression, you should be really adjusting this part. So if I go back to my presentation, I don't know if I have opened that. I told this clearly, and that's why load pull is not required. I'll show you. Because I tried to sell cascade probe stations. I tried to sell Mori stuff. Okay, and I felt, and when experimenters came, then this was really absurd what Modi is doing. Okay, let me show you the match, input output match. I don't know where I showed you match. Okay, over here. Over here. Okay, I'm just drawing one frequency. Okay, sorry. Okay, so one side of this is small signal. You are tuned like this. This is a LNA match. While this is output side. The input side is a small signal match because there the powers are very low. So they are not going to do a lot of excursion. But the output side is going to do a lot of excursion. So this is a small signal match. You are matching under small signal over here. But under power, it should be matched like this. So when you do this, you don't need a load pull to tell you this. You are seeing the impedances with power. Okay, so then Mori is useless if you can see the impedances. So that's what I'm trying to say is that's what you are seeing here. Each one is a frequency, and it looks like more like this curve, right? Maybe it is inverted, maybe it is rotated like this. Okay, so right now you are seeing lots of curve like this. Okay, so if you see here, you're seeing lots of curves like that for different frequencies across power. Now they are all matched for small signal. What about the matching for power? So this guy has to move here. So that means that this guy has to move here like this, not this guy. This edge, this corner should not be tuned. The other corner where you're seeing compression should be tuned. So I guess I have explained to you what's happening with the market. You want to make money, yeah, make money, but and this is what I told you, K is across power. You have to tune it such a way, and you have to stabilize it that for across power and across frequency, the K is it's greater than 1. Okay, and then people have mu also. Well, that is relative stability. Okay, so I don't use mu, because if I use K, I don't have to look at relative stability unless it is very unstable, and I am going to say to a customer that, okay, don't compress more than this. For example, an Astra X band amplifier. You go and look at their data sheet. 40 dBm, well and fine. 40.1 dBm, it will blow up. We cannot guarantee you. It is specifically written in their data sheet. 40.1, it is outside my scope of data sheet. It will blow up. We don't guarantee that. What kind of designer are you? That 40 will be okay and 40.1 will be blowing up. This is what Astra is, because they are using optimizers. Their engineers are using optimizers for tuning. They don't think in terms of stability and all that, in terms of ruggedness and all that. Okay. So let's go back. So have I answered your question?
Yeah, you did. Yeah, thanks.
Okay. So I'm going to close this example. I'm going to go back to my example. Close workspace. And then design practice. Okay. Okay. So we just down this. We were on a LNA. We'll go back to our LNA. Okay. Why this bitterness with me? Because when I started with IBM, you have to deal with people with 20, 30 years of experience. And when you are trying to make a point, they are not ready to listen it against their 30-year baggage. And that was the reason why IBM division doing PA was closed down. Okay, because I was telling for a long time, 1 year advance, I was telling what wrong you are doing, and my manager won't listen to me. That's why my bitterness is there, because you don't work with the baggage, you work with the theory. So if you pick up a book by what is called, John Martin is one book, other book is Gray and Myers. If you go to Gray and Myers and you look at page number 13, they talk about something called what you call current crowding in emitters. Okay, so they were telling that it is not the periphery, it is not the emitter area, which is the periphery, which is important for power delivery, because all the currents are crowded on the periphery. So now I'll tell you this example. This example was the reason for downfall of a division. Not just 100 people were laid off, and I was laid off among them. And the reason was the manager. And I'll explain you, I'll not name the manager, but I'll explain you what he did. Okay. You should not do this. Okay. So we had this HBT with these ammeter fingers like this. Okay. So there are lots of them like this. So ammeter fingers, basically we are talking about ammeter periphery. And so let's say we have a 3000 micrometer square ammeter area. So that was basically length into width. Okay, so that was basically length into width into number of fingers. Okay, so this is total ammeter area. Okay, so what he did was he wanted to cut down on the size of the PA. So what he did was he made this twice the width, and he cut short the length to half. Now the area remained the same. So if I do the same number of fingers, the area remained the same. Okay, area remained the same. He was coming with 22 years with alpha, and he used his head that I can reduce the size of the PA and then I can make more money. Okay, so there used to be, intelligent people. I'll mention intelligent people. Gregory Henderson, who works with, I think, Analog Devices now, and then there was this guy Dong Sing Dong. Okay, these guys were intelligent people, but they were 9/11 at the time. There were lots of people leaving the company, not 9/11, 2000, leaving and joining startups. So all the experienced guys left, and this manager was there with 22-year alpha experience. He cut down the emitter finger into half and made the width twice. So the area remains the same. But what was happening to the periphery? The periphery used to be twice of L, twice of L, twice of width, twice of width in the number of fingers. Now this is called the periphery. And the periphery is halved now. Because the width was doing nothing, the length is now halved. So the periphery now got halved. That means that this HBT will deliver half the power. Now, we took 8 product lines, and we did this with all the 8 product lines. Okay, the production ready part was available, but he said, no, we will cut down on the size of the PA, and then we will make more money. So on all 8 product lines, he cut down the size of the power cell by reducing L to half, increasing W2 twice. And the 13th page of Gray and Meyer says it is not the area, but it is the periphery. So what happened? After 8 months, when we tested the part, they could deliver only half the power. All 8 product lines failed. We were 8 months behind going to market. And all other people went ahead, RFMD, TriQuint, and we lost everything. And this whole division, okay, with 93 people was shut down. This was because of one stupidity. And I'm telling you this stupidity, which a baggage guy will do. And being a new designer, I was reading more of theory. And I said, this is going to deliver half the power. I said this in January, they realized it in November, that what mistake they did. And at that time, we lost the market. So this is the difference between a successful company and a failure company. And this is IBM, okay? So I'm telling you this for a reason. The reason I'm telling you is there is no substitute for theory. Okay, these days, these education institutes, they come and say, oh, we should do, people teach people a lot of, practical stuff. No, you should you should teach them a lot of theory. You should teach them a lot of theory, not practical. Practical comes as a practice. Okay, it's not a part of learning. It's a practice. It's not a part of learning in college. It's a part of learning in a work environment. Okay, you cannot substitute that work environment in your institute. Okay, so the way the education system is going in India, it's totally opposite. Okay, in the practice, but who is going to teach practice? The one who taught theory for 20 years is going to teach you practice. So that doesn't make sense, right? So that's the problem with Indian education system. Okay, I'm going to stop here because we are at 11 o'clock. All I have tried to explain you is we have grounding. We have to worry about how do you take heat out. We have talked about, stability. We have talked about high frequency stability, low frequency stability. So we are going to stop here, though it is going to take, our time, and we are going to slip on agenda. But I feel that when you go as a fresher, okay, and you have a boss on your head, okay, stick to the theory. Don't stick to the boss. This I tell you in SAC also when I go there. Stick to the theory, not to the boss. Okay, I went to analyze a Gilbert cell mixer for down conversion in SAC. And the top guy told this junior engineer, I need a 30 dB isolation between RF and LO. How? The topology won't allow you. And this guy is struggling for 6 months to trying to get a 30 dB isolation on a Gilbert cell using resistors. The best he could get was 9 dB. When I went there, I said that you are struggling for useless reason. It's not possible, right? So stick to the theory if you are a fresher, not to the boss. Okay, so we are going to take a break here, and we will come back and we'll start doing the designs. Just read a lot of theory. That's what I'm trying to tell you. Okay, if there is a question, you can type here, or you can save your question for me answering you. Okay, PDK I've already shared, but I will share it again. Over here, you can download it from here itself. GPDK, sorry. Okay, let's have a break of 10 minutes, and we'll come at 11:10. Recording. Okay, so outband is stable anyways. So I'm going to just look at my band of interest, which is a very narrow band. So I have no difficulty in doing this. Okay, broadband amplifiers. Okay, in broadband amplifiers, there are two options for you. One is the matching you do broadband. The other is traveling wave amplifier. So these are two different concepts, right? And in traveling wave amplifiers, there are waves travel in two directions from any source. One is the forward, other is the backward. So the problem with traveling wave amplifiers is you have to have a directional flow of waves to the output, not backward. That's why the efficiency numbers are poor on a traveling wave if it is just designed by the theory, okay, of a transmission line. You have to use tapered lines to make sure that the waveform is always in the forward direction, and the reverse direction waveform is very less. Okay, so that's the caution in traveling wave amplifiers. So I can do a workshop on amplifiers only, but right now this is not the workshop for that. Okay, where did we go up to? There's a problem here. Where did we go from where? It's not 27 megahertz, sorry. It's 27 gigahertz. Okay, we have to match this. Okay, so I am going to put an inductor, a shunt inductor on the input. So I always start tuning from the input. Okay, why? Because unless you put a power here, what would you tune here? You have to get the power in first, right? So that's why you should do this thing here. So let's pick up a inductor. There it is. Let's see the smallest possible inductor. Well, if you have a shunt, you should start with the largest possible inductor, because that's not going to do anything to your match, right? So you should start with a very large inductor, so that doesn't vary your match. So at this frequency, a 0.5 nanohenry is a large inductor. And then, of course, I would have something like this, because there is no ground. The ground is inductive, right? Okay, so I'm going to put something like this. Let's put an inductive ground here. So this represents a bond wire. Okay, so this is basically a total inductance of the ground which you bring in. Okay, now I have something to tell you. Okay, the thing which I have to tell you is I could have used this ground, right? So instead of connecting this, I should have connected this. But I didn't. Or if I do this, I would have to put something over here, because this is a part of stability, right? This is an inductive ground, understood. But then if I want to be sure that this is stable, let's see if it is stable. Okay, it is stable. It's not that erratic. So fine. So that way it's okay. But you might need stabilization. So you might need another inductance over here, right? Otherwise you are matching to the transistor without the source degeneration, right? So that's fine. For this one, this is doing the good job, right? So that's okay. So now, if I simulate this, I am over here. This guy is over here. It's not behaving as it's supposed to behave, because there will be lots of parasitics in here. So it's fine. Let's work with this side. This has to be reduced. 22. 22. Okay. So this is coming down. Well, this one is over here. It seems like I need a series inductance here, right? So I'll take a small inductor this time. Maybe this is a small inductor. And I'll rotate it and place it over here. So this will move along the direction of the inductor. So it has exceeded actually. So this inductance was too large. 22. Okay, so we are here at the center of this Smith chart. This is over here. Okay, so it's fine. So if I want, I can always use this as a part of tuning, right? So I can do this as, let's reduce this. Okay, and there is this part, and so I have reduced this a lot. So we started with what, 40, right? So let's put here 30. Okay, then reduce the inductance, the capacitance more. So 40 and 40. So when you see the Smith chart, you should know which way the shunt and the series components are going to move you. Okay, so there we are. This inductor has to go lower to move to the right hand side axis. So let's say 35. Okay, so that's fine. So let's reduce this further. 32 and simulate. There you are. And then you need a little bit of more inductance over here. So make this 23 maybe. And there you go. And this capacitance has to be reduced further. So this capacitance has to be reduced further. 12 and 12. Say okay. And say simulate. Okay, there we are. So now we have kind of a good match, right? So let's look at what has happened to the gain and S11 and S22. Okay, so you are better than 20 on the return loss and you are better than 10 on the gain, right? So now I want to design a 20 dB gain LNA. So if you remember, we were doing the receiver side and we had a LNA of 10 dB gain, right? Now we have a 20 dB gain LNA, right? What it's going to do? It is going to lower your overall noise figure of the receiver. So you put more gain on LNA, it is going to lower the noise figure coming from the mixer, right? So that's what I'm trying to do here. Okay, so I want one more stage. So the way to start is for LNA, you start with the input stage because your requirement is not the gain, not the return loss. It is the noise figure. So let's look at the noise figure first. So you go to simulation S parameter. Simulation S parameter. And okay, you don't have to do anything over here. If you want to plot noise figure circles, you can plot noise figure circles. But what I have to do is I have to just, make this active. And all I have to do is simulate this again. But then there is an option because the IEEE standard defines it at 16.85. So there is an option block here. Where is the option? Options. You should set the temperature for simulation is 16.85. Well, people may say that this, if you are going to use a LNA at 25, why do you put 16.85? Well, that's the IEEE standard. So that's why I placed it there and do simulation. And then I'm going to plot the noise figure. So noise figure NF2 is the noise figure. So that noise figure is at around 1.16. Now in CMOS process, you are not going to get this. This is a baby process for baby engineers. Well, the matching was made simple. Oscillations were not there. Then noise figure is so good. Well, this is because people want to, once they get used to, doing this, okay, then the real process is going to be slightly more difficult on stabilization, poor noise, and then you're going to struggle with how to improve the noise figure. Then you are going to work with what is the sweet spot GM, and then what should be the current and stuff like that. Now the question comes is not what is noise, what is the source of noise here? So for that, I'm going to use another presentation which I yesterday showed. Is there a question? Oh, Nazif is there. Okay, noise figure. Trainings. Okay, Noise figure. Wrong one. Open the wrong one. Should open part 2. Noise figure. Maybe I'm still opening a wrong one. This one. Noise figure. Noise. Impedance matching. Where do I talk about noise? Should be talking about noise here. Okay. So I have some background into this. So I'm going to paste these slides over here. Okay, role of an LNA. So yesterday we talked about all this stuff, right? And LNA characteristics, right? And then we talked about stuff. Now there is something about noise here, right? So there are 4 basic noises: thermal noise, flicker noise, short noise, burst noise. Short noise is when you have PN junctions and the carriers take different paths, and then they arrive at the collector or the drain as bunches, right? So there is a certain noise which is called short noise. Now it's a function of current. So if you lower the current, the short noise will go down. Thermal noise. Thermal noise is because of interstitial defects. Whenever you have SiO2 interfacing with silicon at the gate, at that point there are lots of defects. Now these defects, they capture the carriers and then they release it after a certain relaxation time, right? Now in case of electrons with higher mobility, okay, you have this happening more frequent. So and more of it is occurring because that's the electrons are dominant here in a NMOS, right? So NMOS is noisier compared to a PMOS because of the mobility constraint, mobility reasons. Okay, so PMOSs are going to be noisier than NMOSs are going to be noisier than PMOSs, right? So if you increase the area of the gate, okay, then these variations are going to average out. So if you take a large device, your your flicker noise, so flicker noise is going to go down. So flicker noise is because of that the defect sites. Okay, so if you go to PHAMT, for example, then there is no interface between silicon dioxide and silicon. So you are way within the bulk. So in that case, the flicker noise goes down. Now short noise, okay, whenever there is a PN junction, there is a short noise. Now in PHAMTs, okay, the 2D gas is basically near to forward biased PN junction. So 2D gas is a near to forward biased PN junction. That means that it is going to suffer from short noise. It's not going to suffer from flicker noise, but it's going to suffer from short noise. And the thermal noise is because of the resistances. So because of the Brownian movement of these, alloy ions or whatever, metal ions. Okay, so here I'm talking about short noise. And then short noise also has a as a corner frequency. After that, it decays. So if you are designing LNA at high frequency, you are not going to see this short noise because by the time it would have decayed. Okay. Again, it should be a function of current. So if there is a I square, I have removed that expression, but that's a function of current. Okay. Thermal noise is because of this, right? And then flicker noise is 1 by F noise is because of that interstitial defects and all that, right? And then there is a burst noise because now this has to do with whenever you do an ion implant, Like for example, if you take a poly and you want to make it resist, you want to reduce its resistance. What do? You do an ion implant. So whenever you do an ion plant, there would be a burst noise, though it will be very less in case of poly, but it will be still be there because of the heavy ions. It is confined to audio range. So basically it's not going to hurt you in RF, right? So this is going to be, burst noise. So these 4 noises, so I'm going to copy these 4 slides. Okay. Sorry, even this slide, or maybe all the LNA slides. Okay, because I want you to have something. Okay, LNA specifications. Should I talk about specifications? No. Let's go here and paste this over here in this presentation, not this one. The one where I'm using to explain. Okay, so you have all the theory about noise here. So we are designing for a certain noise figure. The noise figure really looks good. For one reason, we are at a higher frequency. For other reason, that this demo kit is basically making things easy for you to have a good design experience initially. Okay, that's fine. So this is my noise figure. Now I haven't done anything for tuning for noise figure. Now there is a little bit of theory which I want to give you on simultaneous match, TANEOUS, simultaneous match for gain and noise figure. Okay. 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 So let's pick up a Smith chart. Maybe this Smith chart, right? And Control C. Sorry, and save this. Save as match. And I am going to just display it over here. Insert picture from this device, desktop, match. Okay, so if I was to do, now this is a match for conjugate gain, actually conjugate match for gain, because you see S11, S22 come to the center, but the noise figure match may be somewhere else. So these are the circles. Okay, so these are called, let's say, noise circles. Okay, so these are these noise circles which are centered around somewhere else. And the center point is called NF min of the device, which is over here. Okay, so this is where the optimum noise is. So this is where I should be tuned. And let's say this is where I tune. So I'm seeing a different noise figure than NF min. Okay, now this is matched for gain. If this was matched for noise figure, my impedance would be over here. Sorry. Okay, my impedance would be over here, right? If you are matched for noise, while I'm sitting at a much worse noise here. Okay, so I could have done this. Okay, I would have tuned for noise figure and let the gain suffer. So I have optimized for this, but there is an issue. So how would I do that? It is very simple. I would go here and introduce the inductance here, and I'll keep on increasing the inductance, and I will, well, you can do the maths also. Okay, what you do is you can calculate the inductance which causes this impedance to look like 50 plus j something, and then the negative, the reactance part you cancel out with the matching. So that way, this circles. So right now, let's just put it over here. Group. Let's keep them over here. And let's say I'm matching for the noise figure. So in that case, okay, in this case, this guy is going to relocate over here. And what I have done is simultaneous match for noise figure as well as for gain. And what did I do for that? For that, I worked with source degeneration. Okay, so I will draw over here only. So what did I do to reach here was I did okay, and I did an inductor here. Well, it doesn't look like an inductor, but I could have made this look like an inductor. Okay. Okay. And okay, so by working with this inductor, what did I do? I want to bring this to match to 50 plus JX. There are many papers you can read about this simultaneous match 50 plus JX. So this inductor brought me to 50 ohm. And then I cancel this JX with minus JX. And I had a 50 ohm match. So what I did was I can bring both circles, basically the gain, maximum gain and noise figure I can bring on top of each other, right? And that too at the center of the Smith chart. So this is the best for gain as well as noise figure. So this is a simultaneous match, okay? And all I have used is the inductance over here. Group. But you should know that nothing comes for free. You have traded off something over here. What you have traded off is compression. Okay, so what you have traded off is gain compression. Insert shape. Okay. So I'm going to do, come on, I shouldn't move that. I should move this guy. Okay, so what I have traded off is the gain compression. Insert shape. Yeah, so earlier I was compressing way ahead, maybe like this. And later later I did this. I compressed much earlier. So you understand that I had a price to pay. Nothing comes for free. So this is what happened. Sorry, come on. Okay, this is what happened when you did this. This is what happened when you did this. This is the price which you paid for doing a simultaneous match. So now, as a designer, you have a choice. You can design for certain compression. Why? Because that is going to decide your TOI, right? Input TOI. So your SFDR is based on compression. Second, your SOI is basically looking at a half IF problem. So if you remember yesterday, I explained you what is a half IF problem. Okay, so SOI basically is bind to this half IF problem. So is this LNA design good? Well, this is good on its own, but in a system it is bad for these two reasons. One is the ITOI, other is half IF problem. This is bad. So usually I don't do this kind of stuff. Okay, I'm not writing a paper for LNA. I want a system, right? So I have to look at the thing which I'm compromising for this kind of stuff. Okay, so having said that, you understood what is a simultaneous match. Now, when you do at the end of it, when you do what is called Monte Carlo on this LNA. Okay, so let's go back to where we were. Okay, and you find that this LNA is failing. Okay, then all you do is just slightly increase this inductance. All the other effects will be countered by just this inductance, and it'll pass the yield numbers. Okay, so well, for LNA, there is one Jack Sifri from Keysight. Okay, he's famous about LNA, and he does this workshop on DOE, and then he takes a classic LNA example and applies DOE to improve the yield. And he does all this stuff over here. I went to his workshop, I just did this. Okay, so you slightly go by like 0.2, 0.3 dB gain, you sacrifice. How does it matter to you, 0.2, 0.3 dB gain? And you just reduce the dependence on this when it comes to yield numbers. Okay, so all that stuff. So in a circuit, what you should be aware of. In a circuit, what you should be aware of, which component is the deciding factor? The most important component, which is a deciding factor, is this degeneration. It's not these. So you can apply DOE for almost 2 days and get your part to be wonderful, or you can do this in 2 minutes. Okay, so we spend 1 day getting the DOE thing and getting this number, meeting the yield numbers and everything, sensitivity and all that stuff, design centering and all that. So at the start of the workshop, I just increased this by slightly by sacrificing 0.3 dB gain. Is my 0.3 dB gain worth 1 day of work? As an engineer, no. As a scientist, yes. Okay, so if you run into problems, the trick is slightly degenerate it, end of the story. Don't kill a lot of your time. Okay, fine. So this is what has happened here. Okay, so we have designed a single stage. Now let's say if I want to do a 2-stage. So now this one is for your noise figure. Now usually what happens is, if I want to deliver certain power, usually I would have another stage following it, which will be for gain. But then the idea is I will increase the transistor size, okay, over here to deliver certain power. But then this is counterintuitive. Why? If I was to use large transistor, I'll use on the input side, not on the second stage. Why? Because I know that if I increase the size of the transistor, my flicker noise is going to go down, right? Okay, so flicker noise is going to go down, so larger transistor will give you a better noise figure. So why would I use it as a second stage? I will use it as a first stage. Okay, so you should understand what is affecting your noise figure, right? So let's say, just for argument's sake, I'm going to save this file as a second stage. Save as stage 2. Okay, and let's say I'm going to take this transistor to 40, so twice the size. Okay, and then I'm going to retune the stuff. Okay, so this window is for the previous one. So let's retune the stuff. I have changed this one. Let's look at the match. Okay, so I will look at S11. I will look at S22. So I'm over here. I'm mismatched now again. Okay, next thing is I want to look at stability circles, because I cannot live without stability. Okay, so I'm going to do here is I'm going to put here stability circles. load stability and source stability. Okay, so they are outside. I'm not bothered. I will put here this guy both. Now I have to do this matching. So now I realize what has happened. What has happened is that this inductor is too small. So I will increase this back to like 40, right? And simulate. It's not doing anything. Oh, so we are on the wrong side. Sorry. I thought, so this is S11, right? So that's the output side. Sorry. Okay. So let's go back. Where was I matching? Okay. So we use a inductor to come up, and then we use a series inductor to go this way. So this series inductor is too high. Well, maybe I don't require a series inductor. How's that? Now see what happens. Oh, we are over here. Okay. And how do I get over there? I would reduce this. And this is already, so let's say if I put this as 24 and simulate this. Okay, so this will move closer and closer. And 20 is the minimum size of with 1.5 turns. Of course, this is the limitation of the process, but what you can do is you can put one inductor if you like. So I'm just going to copy this inductor and put it in parallel. Okay, escape, simulate. Oh, you see what happened to the stability, right? So you have come in now. Okay, so what do I change here? The problem is over here, as I told you, that this was stabilizing it. This is for stability. This is not your ground inductance. Ground inductance is over here. This is for your stability. Make it 20. Fine. Hit simulate. Gone. And we are matched here. So basically this is over here. This is over here. The problem with this guy, sorry, let's down this. The problem with this guy is this. Okay, you have to put it to the left. Yeah, and reduce the capacitance. Reduce this capacitance. 10 and 10. Apply and simulate. What? Oh, I had to increase this. I went the other way. I'm really sorry. It should be around 18. Lower capacity, higher capacitance will move less in cities. Yeah, so we are matched over here. Now, what do you expect with the noise figure? Well, it is biased with the same voltage. So if you see, it is biased with 0.8, right? So it is going to draw twice the current because I have twice the size. The current density is going to remain the same. Okay, so I'm burning more current here. Okay, second thing is that the gate is larger now. So I'm expecting a much lower noise figure on this one. Not much lower, but lower. So this is around 0.76. So as an argument, this should be the first stage, not the second stage, right? This should be the first stage and that should be the second stage. Understood that? Okay. Now let us see if I want to have a two-stage, put stage 1 and stage 2. Okay, so I will save this as, save copy as, okay, I will call this as LNA 2 stage. Okay, and I am going to copy that thing over here. So I will go here to LNA first stage, and I'm going to copy this guy. Okay, do I need this? I don't need this. I won't need this. I won't need this stuff. Okay, Control C. And I'll go to a two-stage here, Control V. And just a second. Okay, we are done. What happened? Did I goof up something? Oh, I didn't even give the supply. So this is your VDD and this is your VG. Okay, now it's okay. Okay, this is NF. This is this, and let's look at the gain and return loss. So gain will be around 20. Right, so gain is around 20. And let's look at S11 and S22. So that's there. So now I have a 20 dB gain LNA with a noise figure of 1.2, and the matching is as good as -20. So this is very simple design. Now the next question is, this is already simplified. Okay, this thing is already simplified. Okay, but then there was a way to simplify this. Okay, usually I spend time in simplifying this, but here, if you see, you cannot replace this capacitor because there is a path to ground. You cannot replace this capacitor because there is a path to ground. Now you have two inductors. Okay, now these two inductors, of course, you cannot replace them. Well, you can replace them with a one inductor. The reason for putting two inductors was that the process didn't allow me an inductor with a radius less than 20. So in this case, what I'll do is, in real circuit, I'll just put a trace of line going to ground. That's it. And that would be done. Okay, so this interstage doesn't need any simplification. But sometimes the interstage needs a simplification. So I will have a small 5-minute note on that part. Okay, so interstage simplification. Okay, interstage is not an art. It is just that, okay, art and magic and all that, if you cannot define it, that's why it's called an art or magic. But if you can define it, then there is no magic or art. Okay, so let me go back to my presentation. Okay, so over here, is this the one I'm working with? Yes. So if I go to the LNA, so this is stage 2. I have a much different matching here for some reasons. And I'm doing a simplification over here. And I simplified to this simple one, which I have already arrived at. Okay, but there is a way of simplifying this. Okay, the way of simplifying this is, how did we reach here? Okay, so if you take the two-stage, okay, so basically you are transforming 50 ohm to what transistor wants to see here as a load. And if you look at the second stage, you have a 50 ohm which is transformed to what transistor wants to see here. Okay, so we are going from R plus JX to 50 ohm. Then from 50 ohm, you are going back to R dash plus JX dash. Okay, so if you see, let me draw it here. Okay. Okay, what did we do? We had, let's say, some match, right? We want to match this on the load side. So this is the first stage. And we were sitting somewhere here. Okay, and then we had a source match, which was way over here. And we were trying to match this to that. But what route did we take? We went from here to here. We went from here to the center. right? So I'll make it dotted and empty. No fill, and that's fine. So we went from here to here, and then from here, we went back to here. So basically, we went through 50 ohm to our other match. Now, if this is overkill, all you needed was to go from here to there, you really practically don't need a match. You need 2 coupling caps and 1 shunt inductor. So all you needed was 1 shunt inductor to go that way. So that is what is happening in our match, right? In our match, okay, you are just needing 1 shunt inductor over here. That's it. In a 2-stage, I am just having 1 shunt inductor. This is a coupling cap. So this is just a 1 shunt inductor, and I'm going from here to there. Okay, so that is the simplified match. Okay, while the other problem is, okay, we went this way and that way, so we are having a lot of loss on the interstage. Okay, so the idea is to minimize that. Now here you can do minimization, but if this was over here or somewhere here like that, you would pass through 50 ohm. So there was no question of simplification. You were passing through 50 ohm, there was no question of simplification. But if you are on same side of matching, you don't have to go to 50 ohm. So the simplification works on this way, that instead of going through 50 ohm, if I'm sitting on the same side, instead of going through 50 ohm, I would rather directly go to the match. So this will not be a 50 ohm system. The interstage match will be a non-50 ohm system. So the interstage matching is not an art. It is not a magic, as the PA guy says. It is just interstage matching. Okay, the way to do this is the following. Okay, so I will not do it here because we are already simplified. Okay, so I can remove this slide. It doesn't say much. Okay, so let's go back to our presentation. Okay, so what did I do for simplification? I wanted to see what a 50 ohm looks like. And in case of a first stage, so all the matching element was this guy. Then I want to see what input looks like on a second stage. So 50 ohm is transformed to something. So I want to look at what are those transformed impedances. So 50 ohm is transformed to load for the first stage, and 50 ohm is transformed to the source for the second stage. Then the transistors are going to be conjugates. So you replace this 50 ohm with the conjugates. And conjugates is the normalizing impedance in ADS. So all you do is you put these impedances, which are conjugates, and build a CLC or any other topology such that both matches come to the center. So what is happening is you are matching both the transistors. Okay, so let me explain you once more if you haven't understood. I am going to see what a driver wants to see as a load, what the second stage wants to see as a source. And then I'm going to take conjugate of both. Okay, because this is what the transistor termination was. And then construct a circuit in between. Okay, such that I come to the center of the Smith chart. Then the equivalent I'm going to place here, and we have a 2-stage. So interstage matching is basically just simplifying the 2 matches to have 1 match and reduce the number of components. That's what the interstage match is. Okay, so I'm going to stop here. It's going to be 12 o'clock. After we come back, we will start with digital phase shifter, right? So let's get back to the progress, and I'm going to do a pause recording here. Just a bit. Okay, if you have a question or if you have a suggestion, type it in here in the chat box. I am going to just look at what happened to my outline. We are over here. And I guess I have discussed all this stuff. Okay, now I am jumping to over here, digital attenuators and phase shifters. So I am going to jump to here. and to here. Okay, and then come back and do these two. So I'm trying to cover as much time I can to finish it tomorrow. Okay, so please, if you have a question, type here. If you want to ask a question, right? And I would like to, solve it if I can, right? So we'll take a break. I'm going to stop the recording for first two sessions.